Sound is working? Yes. That sound good? Okay, don't need to do a test. Fantastic. Well, we had a visitor last week, a professional artist, and I just wanted to show you some of her artwork. This is all done with wires, and I thought she did an amazing job just depicting the crucifixion of Christ on the cross with all the people, Jesus' followers gathered around and seeing what was happening there on the cross. Very appropriate for Palm Sunday. And, I love the service that was this morning. And I like the linking of Zechariah 9 with Matthew 21. And, Zechariah is amazing in that it predicts in detail a lot of the things that would happen towards the end of the life of Jesus. How we'd be sold for 30 pieces of silver, and what those 30 pieces of silver would be used for to buy a potter's field, a field for burial of poor people. That was predicted by the prophet Zechariah more than 400 years before the event actually happened. But as we heard this morning, Zechariah also predicts that when Jesus enters Jerusalem, he will come on a donkey with a colt. And when you read Matthew 21, that's exactly what happens. Jesus comes in on a donkey with a colt following. Now, I got a question for all of you. When Jesus comes back a second time, what kind of animal is he going to ride? He rides a white horse. Okay. I mean, Jesus was riding a donkey. Why did he need the colt? Ever thought about that? Why? Because both Zechariah and Matthew talk about this colt that accompanies the donkey that he rides on. Why the colt? Well, what will a colt become? A horse, right. Okay, so what was Jesus communicating when he was riding the donkey? And we heard this morning that when the donkey is a symbol of peace. I mean, to give you an example, when you go into battle, you don't want to ride a donkey into battle. The reason why the donkey, when it's bonded to a human being, is highly motivated to keep you away from danger. This is why they have you ride donkeys when you go down the Grand Canyon on that very steep trail. Because people know that donkey is going to do everything it can to make sure that the human rider doesn't fall over the cliff. Horse, it's a different matter. But the horse is the animal you want to take into danger. As it says in the book of Job, chapter 39, the horse is the animal that loves to take you into adventure and danger. And so a horse actually relishes taking you into battle where bullets are flying at you, arrows are coming at you, spears. What happens with a donkey, as soon as it sees a spear or an arrow, it heads in the opposite direction. So there's no way you're taking a donkey into battle. But that's why in ancient times, people understood the donkey is a symbol of peace. The horse is a symbol of war and conquest. And as you heard this morning, the Jews were expecting the Messiah to come as a conqueror to deliver them from the oppression of the Romans. But instead, he came in on a donkey. But behind the donkey was a colt. And basically, it's communicating to all those Jews, this isn't going to be the first time I come into Jerusalem. There will be another time. And that's kind of the big difference between Christianity and Judaism. Judaism believes that the Messiah comes once and only once. Christianity, he comes twice. The first time he comes as an instrument of peace to sacrifice himself for the sins of the whole world. The second time he comes as a conquering king. And for the Jews were hoping that everything would be in one coming. But with that little colt behind him, he's basically communicating the point. I'm going to come back, not on a donkey, but on a horse. And it's not going to be now. It's going to be future, because it's going to take time for this colt to become a horse. And so he's going to come on a full-grown white horse at the end that you see in the book of Revelation. Okay, before we jump into our study of Isaiah, and by the way, I'm going to be putting you all to work, okay? So just get ready. I got some assignments for you. But before we get there, last week I promised I would share with you a discovery that got published about planetary magnetism. It's a phenomenal paper. It got published in the May issue of the monthly notices of the Royal Astronomical Society. You say, hey, it's not even May yet. We're still in April. And then we're not even at the middle of the month yet. But that's the way the monthly notices of the Royal Astronomical Society does. They actually release papers a month in advance of the present. So this paper is actually being published next month, but it's already released. And I got the paper here if you want to take a look at it, written by 3 Australian astronomers who basically begin their paper by saying, we live on this planet not only with a strong magnetic field, but a permanently strong magnetic field. We've had a strong magnetic field for at least the past 3 billion years, maybe back as far as 4 billion years. And we also know that our magnetic field is critical to have life here on planet Earth, in this sense, that if you don't have a magnetic field, then radiation from the sun begins to ionize the molecules in our atmosphere. And one of those molecules is water. And when it gets ionized, what happens is you wind up having the hydrogen being separated from the water and or the oxygen, and it gets dissipated to outer space because Earth's gravity can't hang on to the hydrogen. And so we get a loss of water. And it's gradual, but over time you wind up with a bone-dry planet. This is thanks to our magnetic field, we got to retain our water. And thanks to the magnetic field, we don't get killed by deadly solar radiation, and we don't get killed by cosmic radiation. If you want to know what our magnetic field looks like, it is kind of complicated. And what happened to our visual here? If we lost... Okay, let's see if we can get this back up and running. Hopefully the live streaming people are seeing it. It's just you here that can't. Oh, here we go. Okay. This was all working fine a few minutes ago. This is our first time here in this room, so expect a few technical difficulties. I'll tell you what, while they're working on the technology, I'll just assume that you can follow along, and we'll get these visuals up in a minute. But yeah, we have a very complex magnetic field, strong magnetic field. By the way, it does vary. Gee, almost had it there. Our field right now is about 1 Gauss. It gets as weak as about half a Gauss. Sometimes it gets as strong as about a Gauss and a half. But it never goes down to 0. We stay well protected. And the way the magnetic field works is it actually forms a magnetosphere around the Earth. And I got a nice visual of the magnetosphere once we get these visuals up and running. And so basically, we live in a magnetic bottle. Because of the magnetic field that the Earth manifests, we wind up having this magnetic bottle. And it's such that when deadly particles from cosmic rays and the sun impinge upon the Earth, they get deflected by this magnetic shield that's about the Earth. And as long as we're inside that magnetic shield, you can have life that's more complex than microbes. There is some speculation that maybe 4 billion years ago our field wasn't as strong, but there again you're dealing with microbes that can actually withstand a lot more radiation than we can withstand. In fact, they cite a paper that basically says they think the magnetic field at the origin of life was approximately about half the strength that it is today. Would provide some protection. This is what our magnetic field looks like, north and south pole. And we actually have reversals. And so there are some rocks that show as many as 16 different reversals of the magnetic field. Now, it's not the magnetic field disappearing. It's the polarity changing. Where instead of the north-south being oriented this way, it's oriented this way. And so those kinds of polar flips happen anywhere from about every 10,000 years to every several million years. And this is designed to show how the polarity flips work, where you got the North Pole stuff being the blue, the South Pole stuff being the gold there. But this is what our magnetosphere looks like. It actually forms a little magnetic bubble, and you got that blue thing here, which basically is a bow shock that forces the particles to divert around the Earth. And if you really want to be safe, you want to be in this region where you got the red lines. As long as you're inside where you got the red lines, you're being protected from the deadly radiation. If you move outside the red lines and are still in this blue line, you do get some protection, but you don't want to be outside the red lines for a long period of time. So for example, when we send the Apollo astronauts to the moon, for a good chunk of the way, they're well protected by the magnetic bubble that's around the Earth. They do get outside of that bow shock where they're fully exposed, but when we sent astronauts to the moon, we made sure the time for full exposure was only a day, at most a day and a half, and then we get them back under the protection of that magnetosphere. Now, the reason why Earth has this magnetosphere is that we have a dynamo in the center of the Earth. I mean, if you look at the interior of the Earth, and I should have given you a diagram of this, but in the interior of the Earth we have a solid metal core, and there's two theories that the solid metal core is mostly iron with quite a bit of nickel and cobalt to accompany it. Those are all magnetic elements. That's one theory. The other theory is that actually inside that is a uranium core. A uranium core surrounded by a solid core of iron, nickel, and cobalt. Those two models are still being sorted out. But beyond that, outside the solid core, you have a liquid core. And that liquid core is basically made up of iron, nickel, and cobalt. And they're ferrous metals, which means they're magnetic, And because the Earth is rotating, you actually get the movement of this liquid iron, cobalt, and nickel, and that's what establishes our magnetic field. It's crucial that our planet be rotating relatively quickly for this to happen. Well, what these 3 Australian astronomers did is they said, now we've discovered nearly 4,000 planets outside of our solar system. Let's determine how many of them have a magnetic field that's adequate that you could have actually have plants and animals on that planet. So they basically said we're wanting to look at the habitability of planets. And they're basically making the point, if you don't have a strong, long-lasting magnetic field, you're not going to have anything beyond the very hardiest of microbes that can withstand radiation. And even they won't be able to last very long because eventually your planet loses all of its water. So what they did is they looked at a piece of theoretical work that was published in 2006 by a couple of astrophysicists who basically came up with a dynamo model that could be applied for other planets. And these 3 Australian astronomers made some assumptions. They used this model that had been produced in 2006. They assumed that these rocky planets they're looking at, and only the rocky planets would be candidates, that they would have fast rotation and that they would have a dynamo inside. In other words, it'd be liquid material inside. And they point out in the paper those assumptions are very optimistic. But even assuming the most optimistic of assumptions about what these extrasolar rocky planets are like, they discovered that about half of them have no magnetic field at all. And that the rest of them either have no magnetic field at all or they got a very weak magnetic field. And they only found 1 planet in the entire catalog of known extrasolar planets that had the possibility, not the probability, but the possibility of a strong magnetic field. And it's this planet here, Kepler 186f. This is an artistic rendition. This is not a photograph. This is what an artist thought it might look like. And what you see over at the right is kind of an artistic rendition of this planet, Kepler 186f. And by the way, the F means it's the 5th planet discovered in the system. The star always gets the designation A. So this is a star here, this little bright dot here. That's Kepler 186a. And then there are 4 other planets, here, 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 and here, that accompany planet F. And these other 4 planets are much closer to the star and smaller than 186f. The reason this has gotten a lot of attention in the scientific literature and even on the web is this is considered to be the most likely planet on which life could exist outside of planet Earth because it's in, quote, the liquid water habitable zone. But a blog I'm bringing out tomorrow on my Today's New Reason to Believe is basically saying, yes, this is the one they think is most likely, but for a number of reasons, it's not a candidate for life. And as these authors point out, number one, it has the possibility of a strong magnetic field, but not the probability of a strong magnetic field. I mean, after all, we have to assume a lot of things that are probably not the case, but it has the possibility. But there's several other things. As you notice here, this star isn't very bright. How bright is it? It's 5% as bright as our star, the sun. So, and it's orbiting that star about the same distance that Mercury orbits our star. And so, yes, it is warmer because of how close it is to a star. However, assuming that it doesn't have a really thick atmosphere, the temperature on the surface of that planet, let me get that for you here. I actually wrote it down. Okay, where's the temperature? Here it is. Minus 85 degrees centigrade, or minus 121 degrees Fahrenheit. That makes it a little bit colder than Mars. So as cold as Mars is, this planet be colder. However, the people really pushing to make this, quote, a habitable planet are saying, well, if we got a thick enough atmosphere, we can warm it up. If we got enough greenhouse gases. Well, I actually calculated how much greenhouse gas you need. You need 1,300 times as much carbon dioxide as what Earth has, and that assumes you got 10 times as much nitrogen, because nitrogen actually enhances the greenhouse effect. Now, if you don't have that much nitrogen, you need 13,000 times as much carbon dioxide. Okay, now, if you add that all up, that means you're looking at a planet where the atmosphere is so thick, even though it might be the right temperature, lungs are not going to be able to function. Okay, are you all breathing pretty well here? I hope you are, okay? One of the remarkable things about planet Earth, we got exactly the right air pressure for maximum lung function. And you say, well, do we need lungs to respire? No, you don't need lungs to respire. We have other animals that use different means of respiration. But lungs are by far the most efficient means for respiration. If you want animals that can do something besides sleeping all the time, you're going to need lungs. In fact, there's been several papers published making the point that it's not possible to build a more efficient respiration system than the lung. But for the lung to be able to allow you to do more than just sleep on the couch all day, you're going to need the air pressure to be no more than a factor of 3 from what it is at sea level. And so you notice this, those of you who have done some mountain climbing, as I've done, you discover as you go up a mountain, it gets harder and harder to breathe because the air pressure is less, and the lungs have to work harder in order to get the oxygen you need in order to keep going up the mountain. And if you go up to about 14,000 feet, the air pressure is about half what it is at sea level. But if you go up as high as, say, Mount Everest, it drops down to about a third. And that's what you notice. When you hit 26,000 feet, the air pressure is only a third of what it is at sea level. By the way, I think half is something like 16 to 17,000 feet. So that's... But the whole point is, once you hit 26,000 feet, the air pressure is not adequate for your lungs to function, and that's why you need oxygen when you go up K2 or Mount Everest. Or if you go up without oxygen, you better get up there in a hurry and get back down in a hurry before you die. They call it the death zone, because once you get above 26,000 feet without oxygen, your brain is literally dying on a minute-by-minute basis. So, if you've always wanted to go to the top of Mount Everest, I would strongly encourage you, find something else on your bucket list, because you will come back damaged. And a lot of people don't make it. 26% of professional climbers who go up Mount Everest die on the mountain. By the way, for K2, the death rate is a little over 40%. I mean, why would you climb a mountain where the statistical average is 40% die, where these are some of the best climbers in the world? But it's because the air is so thin. Now, I've been to the Dead Sea. The Dead Sea is, 1,300 feet below sea level. What's interesting when you go to the Dead Sea, of course, it's always fun to actually get into the Dead Sea and try to float. It's quite challenging because of how much salt is in the Dead Sea. In fact, they have you go in where there's guardrails, because if you flip over, you're probably not getting out, because you're basically floating so high. But the other thing that was fun for us to observe when we were there is just experiencing how much harder your lungs have to work, because the air pressure is a lot greater than it is at sea level. Now, you can still walk around, but you actually can notice the effect. Now, if the air pressure goes up, say, a factor of 3 above sea level, your lungs cease to function. So this is the problem with people trying to say, well, we'll just alter the air pressure a little bit. Well, you can alter the air pressure, and that might be fine if you're a one-celled fungus or a one-celled bacteria. But if you're an animal, you're going to need the air pressure to be fine-tuned. So that's one reason why this is not a candidate for advanced life, and probably not a candidate even for primitive life. The other problem is it's going to be tidally locked. And The tidal force between a star and its planet goes up with the inverse fourth power of the distance between them. That explains why, for example, the moon is tidally locked to our planet. If you haven't heard of that term, tidal locking is where the rotation period is identical to the revolution period. And so it takes 29 days for the moon to go around the Earth, and it takes 29 days for it to rotate. And for that reason, we only see one side of the moon. In fact, the tidal force that the Earth is exerting on the moon is so strong that the solid rock on the near side of the moon is bulged out by 150 feet. Now, our rotation rate has been slowed down by the tidal forces we experience from the sun. The sun, as far as away as it is, contributes about half the tidal force that the moon does on the Earth. And the combination of the moon's tidal force and the sun's tidal force has slowed down our rotation rate from about 3 hours a day to 24 hours a day over the past 4.5 billion years. And incidentally, we are headed towards tidal locking. There will come a time when the tidal forces of the sun and moon actually make our rotation rate the same as our revolution rate. I wouldn't worry about this in terms of your investment strategies. It won't happen for another 40 billion years. Okay. And there are much more nastier things that will happen before that 40 billion years takes place. But it is also such, because the force goes up with the inverse fourth power of the distance, if you were to make the Earth just 1% closer to the sun than it actually is, we'd have a problem with the tidal interactions. We'd wind up with a rotation period so long that it'd be extremely hot in the daytime, extremely cold at night, so extremely hot in the daytime and so extremely cold at night, no animal will be able to live in the face of the Earth. We're barely far enough away to prevent that from happening. And incidentally, it has happened to both Mercury and Venus. Now, Mercury and Venus are not perfectly tidally locked, but you do notice that their rotation period is roughly the same as a revolutionary period, to within about a factor of 2. And so you have a very long day on both Mercury and Mars. And if you go to Mercury, by the way, Mercury is the only other rocky planet in our solar system that's got a magnetic field. But it's only 1% as strong as Earth's magnetic field. So weak it does not provide adequate protection. So weak it didn't keep the water that was on the surface of Mercury. It's all escaped to outer space. And moreover, because it's only 1%, it's leaky, which means there are times when the radiation just comes in unimpeded. Earth's magnetic field is strong enough that it doesn't leak, and so we're continually protected from that radiation. But this planet, yes? Got a question?
Yeah, I see we're about to use
Yeah, when you get the microphone, I'm going to encourage all of you, put the microphone close to your mouth. If you keep it far away, we're going to get some feedback.
Is
So
this
go
close
ahead.
enough, or?
A little closer, please.
Because I don't want to go like this.
No, that's perfect. That's where you want it.
You're kidding.
I think that way our live stream people will be able to hear you.
Okay, so
Yeah, thank you.
when it's just a little short question. When you're talking about fine tuning and things like that, after you finish that, I'm dying to hear if there's any theological implications about this recent photo they released of the black hole. But you can maybe talk about that when you're done with this. I'm sorry.
Well, yeah, I've put several posts on my Twitter and Facebook page about the black hole, and I guess it's getting a lot of attention because I couldn't believe how many people have read my what I wrote. So I will address that briefly. Let me wrap this up and I'll get to the black hole. Okay. Bottom line is, this planet is so close to its star that even though the star is only half the mass of our star, the sun, because it's just the distance. Am I stepping on something that's causing a problem? Okay, I better not do that. Sorry we lost the visuals again. So we'll get that back. Anyway, it's such that we know the fastest it could be rotating is about once every 10 days. Okay, if it's rotating once every 10 days with an atmosphere similar to what we got here, that means it's so hot in the daytime, water is boiling. and so cold at night that it's like 200 degrees below zero. Incidentally, that's the way our moon is. Our moon's got a rotation rate of 29 days. And remember when we sent astronauts to the moon, they had this big thing on their back? That big thing on their back was a climate system. It weighed 250 pounds, but it basically was a heating and air conditioning system. So that when it was 200 degrees below zero, the heat would come on and keep their bodies warm. And when it was 200 degrees or 300 degrees Fahrenheit, it would cool them down enough that they'd be able to keep going. And incidentally, they appreciated the extra weight because the moon's gravity is only 6%, and having an extra 250 pounds actually makes it a little easier for you to move around. Doesn't work here on Earth, but it works great on the moon. Okay, but if it's rotating once every 10 days, in fact, what you'll see is it's probably rotating between once every 10 days and once every 100 days. Bottom line, that's too slow a rotation rate to get a dynamo going in the interior of the Earth. And what the paper closes with, we may be living on the only rocky planet in the galaxy and probably in the universe that has the kind of magnetic field that makes possible the existence of plants and animals or the equivalent of human beings. So that's the fine-tuning argument. That's the theological implications. It adds to the rare earth doctrine. And basically these three authors are saying Earth is a lot rarer than what we thought before and may indeed be totally unique in its capacity to sustain life. Okay, but no questions about this. There is an article I'll be releasing tomorrow morning at 5 a.m. It'll be up there that you can look at with all the visuals. But I will address your question about the black hole. And again, I couldn't believe how much attention this has been getting. What happened on Wednesday is astronomers released the first ever image of the event horizon of a black hole. Anybody know what an event horizon of a black hole is? Okay. Anybody want to take a stab at it? You know what it is. Okay.
That's where nothing can escape the gravity of the black hole.
Right. Okay, you got this black hole. The event horizon is the distance from the center of the black hole where if you cross that point, you're not getting out. And that includes even light. So if a photon hits the event horizon, it's going to get sucked into the black hole. And anything that gets sucked inside the event horizon cannot be taken out, at least not in a reasonable time period. We'll talk about that in a minute. But what happened several years ago, a group of radio astronomers said, you know, we got these radio telescopes all over the planet. We can link them together through what's called very long baseline interferometry and actually build the equivalent of a telescope that's 6,000 miles in diameter. And with a telescope 6,000 miles in diameter, we can get really high angular resolution. I mean, that's a principle in astronomy. The bigger the diameter of your telescope, the more detail you're able to see. And with this instrument, they're getting down to close to a thousandth of an arc second resolution. To give you some idea what that is, think of the moon. It's 30 minutes. You're getting down to 1 part in 30,000 on the details on the surface of the moon. That's how powerful this instrument is. You say, well, it's at radio wavelengths. Why don't they do this at optical wavelengths where you got a shorter wavelength? The problem is at optical wavelengths, our atmosphere only gives you the amplitude information of the wave. At radio wavelengths, the atmosphere doesn't disturb the position of the wave. And so we get both the amplitude and the position of the wave to high precision. And the way this technology works, at each radio telescope, you got a very accurate clock. A clock that's actually much more accurate than an atomic clock. We use things like hydrogen maser clocks. And if you measure the time very accurately, you can actually line up the phase of a wave at a telescope 3,000 miles away with the phase of your telescope that's at your appropriate distance. And they've been doing this kind of technology since 1967. Matter of fact, I was part of the first effort to, the Canadians were the first to actually develop this technology. And I was kind of the guy who was basically just working behind the scenes. I just finished my undergraduate degree, and during the summer between undergraduate and graduate, the Canadians pulled off the first very long baseline experiment. And when I was at Caltech, I was involved in an experiment as well to use that. But now they have literally a dozen radio telescopes around the world that they link together. You do need to have reasonable weather at all the different sites. And one reason what they talked about with this image is they're actually able, matter of fact, I think I can pop the image up for you. Let me see if I can get that for you. Actually show you, because how many of you ever seen the event horizon of a black hole before? Okay, let me see if I can find it. And I'm finding it quickly. Okay, you're going to have to go online and see it. I thought I had it right here, but it's actually off on this other screen, so sorry about that. Okay, what it does look like, what they did publish on Wednesday, it kind of looks like a donut of light. And you see a little dark spot in the middle. That's the first time they've actually seen a dark spot of a black hole. Now, what happens is, as the black hole is sucking matter and energy into its event horizon, just outside the event horizon, you get very fast movements, because basically you got this material spiraling inside to the black hole, and it's moving at such a high velocity and under such extreme gravitational forces that the matter that's getting sucked in gets converted into pure energy with about 10 to 11% efficiency. Now, to put that in context, the sun, when it's fusing hydrogen to helium, converts matter into energy with 0.07% efficiency. So we're talking about something that's orders of magnitude more efficient than what happens in stars. And in fact, the energy outside the event horizon of black holes is the brightest radiation we see anywhere in the universe. And that's basically what a quasar is. Quasars and blazars, what you're looking at is stuff being sucked into supermassive black holes just outside the event horizon. And the image that was released, and go online, put in any search engine, event horizon of black hole, the image will pop up for you. Basically shows you this orange colored donut with a little dark circle in the middle. But it's the first time that dark circle's been imaged. And I'll add this point to you. They didn't exactly image the very edge of the event horizon, but they're able to determine that that little black donut hole they found was 2.6 times bigger in diameter than the event horizon. And they kind of apologized and said, well, this is the first photo that we've developed, and we ran into some challenges in trying to get the observations we needed, but just wait, we're going to get you better images. And moreover, what they had advertised 2 years ago is that the first image that they're going to release was the event horizon at of the supermassive black hole in the center of our galaxy. But what they released instead was the image of the supermassive black hole event horizon of the galaxy M87. And people have been asking me, why did they do M87 and not our own galaxy? And I said, well, they're actually going to release the image of our galaxy. But they found it was actually easier to get the image of this galaxy that's 50 million light years away. Why? Because it's got a much, much larger supermassive black hole. In M87, which is a supergiant galaxy in the center of the Virgo cluster of galaxies, its black hole comes in at 7 billion times the mass of our star, the sun. Our galaxy, it's only 4 million times. Now, 4 million is still a lot, but what you're dealing with is a factor of 2,000 times more massive, and because of that, it was actually easier for them to get the image of that supermassive black hole. Wait for the microphone. We got a microphone coming to this guy?
I can speak really loud.
No, we want you at the microphone. Again, please, there's many more people involved in this class than what's actually here in person. And so please, let's give some consideration to those that are live streaming. Go
Thank
ahead.
you. I just wanted to ask, is there any way that one of these black holes could cause like a Big Bang type event? Probably not, right?
Well, I get that all the time. People are worried that, for example, the Large Hadron Collider in Switzerland and France, they're going to make a mini black hole. It's going to suck us all into it. But as an astronomer, I can tell you, we are observing energy densities in the universe that are thousands of times greater than anything we can possibly do in a particle accelerator. And they're not doing us any damage. So don't worry about what those physicists in Switzerland and France are doing. They're not going to kill you. How about those black holes? Well, okay. What is interesting is that this black hole event horizon that they image is 7 billion times the mass of our star, 7 billion times the mass of our star, the sun. It's also a galaxy that's 10 times bigger than our Milky Way galaxy in terms of its mass, and it's collapsed. And so in our galaxy, you've got these spiral arms that disperse the stars widely. In M87, the spiral structure collapsed billions of years ago, and you've got this very compact structure. What does that mean? That supermassive black hole is eating lots of stuff all the time. And if you go on my Facebook page, I actually show you a zoom-in set of photos in M87. So the first photo I show you is basically a photo made by the Canada-France-Hawaii telescope, which basically shows you the entire galaxy and its huge family of 12,000 globular clusters that orbit about it. And then the second photo I show you is where you look at the core. When you look at the core, you can see a little jet coming out. Then the third photo, I actually go inside and you get to see this huge bright spot, which was the best image we had of a black hole before this was released. But all you see is a big bright dot. The resolution is not enough to show you the little black donut hole. But it shows this powerful jet beam coming out, basically making the point, this black hole is eating so much matter at such a great rate that there's so much energy being released outside the event horizon that causes this powerful jet to beam out. Now, if we, of our Milky Way galaxy, were any closer to the center of the Virgo supercluster than we are, we human beings would be toast. We're far enough away. And this just got published. It was called the Supergalactic Habitable Zone. You have to, if you want advanced life, you have to be in a galaxy that's far away from these really big supermassive black holes. And that's the closest big supermassive black hole. And we're barely far enough away that it doesn't do us any damage. And what's interesting about our Milky Way galaxy, it's a big galaxy weighing about 1 trillion times the mass of our star, the sun. Galaxies that big have black holes in their cores that are much bigger than ours. So one of the enigmas of our Milky Way galaxy, it's a big galaxy with a tiny supermassive black hole. But if that wasn't the case, for advanced light to be possible, you have to be living in a big spiral galaxy. But it needs to be a big spiral galaxy with a tiny supermassive black hole. If you think 4 million times the mass of the sun is tiny, but it is, and where you're far enough away from that black hole where you don't get killed. There's even more fine-tuning. Our star orbits about that black hole by about 30,000 light years. And if we were like other stars orbiting at that distance, that black hole would do us in. But what's interesting about our star, as it orbits about the center of our galaxy, it goes up and down relative to the galactic plane by only a tiny amount. All the other stars at the same distance are going up and down like this. We go up and down like this. Because of that, we stay shielded from the deadly radiation of that supermassive black hole. So, all that's in the post that I put on my Facebook page. In fact, there's 2 posts you'll see on my Facebook page where I go into these details. Go ahead.
Yeah, you started to address my main question here, which was how big, image scale-wise, that picture that we saw in the newspapers, or which you're referring to, relative to the entire size of the visible view of M87, which is one of my buddies I look with my telescope all the time, and I just don't get a feeling for how small that really is. But I'd also like to ask, why is it that we're able to see that hole when we got a basically spherically symmetric, I presume, sphere of that strong radiation, which should cover up the black hole on the near side?
Well, well, as you're probably aware, I mean, we see this with other astronomical phenomena too. You have all this radiation spherically being emitted, but where is the radiation going to be most strongly emitted? On the edge. That's where you get the greatest thickness. And so if you're right in front of the black hole, that's where you're going to have the least radiation coming in. But you are right. From our telescope's perspective, it's not purely black because you've got some stuff coming out there as well.
That's kind of what I thought.
It's just that it's not as bright as what you see on the edges. And so the photo they release basically shows you that little dark spot. But what's interesting, this is the very first time that astronomers have been able to actually see that dark spot in the center of that bright sphere. And that's why I posted other photos of M87, basically showing you the highest resolution photo that was taken of the core of M87 before the release of this image. And basically you see this tiny, very bright sphere with this jet coming out of it. This one is at such high resolution you can't see the jet, because the jet actually gets ejected a little distance away. So this is just right in at the very core. You're looking at a few milli-arc seconds. That's the whole diameter of the image you're seeing there. Now, they're telling us that within a year they're also going to release the image that we see in our supermassive black hole. They've been accumulating data on that, and so we're going to get that. Now, where the apologetics comes in, and I actually wrote about this in the 4th edition of The Crater and the Cosmos. This Event Horizon Telescope, all these radio telescopes they link together, if they keep accumulating data, eventually they're going to be able to give us images of the event horizon with such high precision, it's going to actually tell us what's happening in the quantum gravity era. You say, what's that? Okay. That's that very early history of our universe, where the universe is so small that the forces exerted by quantum mechanics equal or exceed the force of gravity. That happens when the universe is between the creation event and 10 to the minus 43 seconds, which is 1/10,000,000th of a trillionth of a trillionth of a trillionth of a second after the creation event. Once you get there, gravity dominates everything, and we got a very good understanding of the dynamics of the universe. The mystery period is between 0 and 1/10,000,000th of a trillionth of a trillionth of a trillionth of a second. And so physicists and astronomers and atheists and Christians have been very eager. What is the physics of the quantum gravity era? I mean, there's a famous physicist at Caltech, an atheist, Sean Carroll, who's made the point. He's actually published what he calls the quantum eternity theorem, where he says, if the quantum space-time fluctuations are extremely large in the quantum gravity era, there's a possibility that we can come up with a different conclusion than the space-time theorems, which tell us there's a causal agent beyond space and time that created space and time. But it requires that these quantum space-time fluctuations be very large. There's another paper published by a Christian theoretical physicist, Aaron Wall, and he put it online so you can read it for free, where he says, if we just have those quantum space-time fluctuations at a medium size or a small size, the space-time theorems hold all the way to t equals 0. And so it'd be really great if we could actually calculate or determine how big those quantum space-time fluctuations are. A possibility, maybe even a probability, but not a definite conclusion, is that if we get detailed observations at what's happening just outside the event horizon of a black hole, it will tell us how big those fluctuations are. There's another way we can determine that, and that's looking at the images of distant quasars and blazars. If those quantum space-time fluctuations are large, that means over the distances at which we observe these quasars, it will slightly blur the image. Hey, somebody actually got the image online. Okay. And then we've already done measurements on quasars that are 3 billion light years away at ultraviolet wavelengths. We see no blurring, which indicates that the quantum space-time fluctuations aren't extremely large. However, it'd be good to actually get observations at X-ray wavelengths at 10 billion light years away, then we could really get a good limit. But another way is to count on the Event Horizon Telescope getting us sharp enough images that we could actually use that to determine what quantum gravity speculations are possible and which ones are not possible. And yes, that would have theological implications. Anyway, this is all on the my web article at my Facebook page. Okay. Yes.
There's another question. This one comes from Caleb from the cyberspace. Did European scientists find evidence of life in the Mars meteorite ALH 77005?
Well, on my Facebook and Twitter page, I answered that question. That came up just a few days ago. And you'll probably recall, it was when Clinton was still president. They found this Martian meteorite, ALH 84001, and on national television, he did a little dance around this meteorite, saying, hey, maybe we got the signs of life in this meteorite. And after about 3 years of study, the astronomers basically said, no, we don't think we got the signs of life. This is all something that's much more likely to be abiotic. And my response about the European study is, it's the same thing as what they saw in ALH 8400, or 84001, namely that if you actually look, you can see that there are chemicals that life probably could be responsible for, but those chemicals can also be explained by abiotic process, by non-biological process. They found structures that could be the fossils of parts of of these microbes, but you can also get those shapes from abiotic processes. So they're basically referring to possibility along different lines and say, if we add up all the possibilities, maybe we got a probability. But it's kind of like, if you got a possibility of 1 chance in 100 that is biotic, and you multiply it by 1 chance in 100 that's biotic by a different mechanism, you get a smaller probability. And that's the reason why astronomers eventually said, no, we don't have anything in this Martian meteorite. And moreover, trying to claim that this billions-of-year-old Martian meteorite actually has the signs of life that remain today, that's a stretch. Why would it be preserved at all over that time period? And also, the problem with Mars is that you cannot have a naturalistic origin of life on Mars. The reason why is you've got what's called the ultraviolet oxygen paradox. If early Mars, and by the way, there is a consensus now that there was a time when Mars was warm and wet. And they say if it's warm and wet, life could possibly exist there. However, we know it was warm and wet for just a brief moment of time, because Mars does not have the plate tectonic activity that Earth does. And so if you got carbon dioxide and water in the atmosphere, that's what you need to make Mars warm. You have to have lots of greenhouse gases in the atmosphere. And when Mars was very young, namely 4 billion years ago, it wouldn't have lost that stuff. So you would have had water and carbon dioxide, both powerful greenhouse gases, that would have trapped the heat of the sun. The problem is water reacts with the carbon dioxide to make carbonates. And so Mars suffers what's called the carbonate crisis. That if you ever have liquid water and carbon dioxide, they'll react and make carbonates. And you say, well, didn't that happen on the Earth? It happens all the time. Water reacts with carbon dioxide to make carbonates, but because Earth has such strong, long-lasting plate tectonics, the carbonates get returned to the atmosphere as water and carbon dioxide. That return doesn't happen on Mars, and so for the past 4 billion years, Mars has been cold and dry because of that carbonate crisis. The other reason why we know that you can't have life on Mars 4 billion years ago is the oxygen ultraviolet paradox. If you got oxygen in the atmosphere, that stops prebiotic chemistry. If you don't have oxygen in the atmosphere, you won't get ozone. And if you don't have ozone, ultraviolet radiation comes in unimpeded to the surface of Mars, and that ultraviolet radiation is just as catastrophic as the oxygen to any kind of origin of life chemistry. That famous Urey-Miller experiment where they put carbon dioxide and water and ammonia in a flask and sparked it, and they got glycine, the simplest of the amino acids. They were scrupulous to make sure no oxygen. Even the tiniest amount of oxygen, you get nothing. And they're also scrupulous to make sure no short wavelength ultraviolet radiation, because that also stops the prebiotic chemistry. With Mars, that is in full force, and so Mars is not a candidate for the origin of life. Therefore, a meteorite from Mars is not a candidate to have life in it. And that's what happened in the days of Bill Clinton. They finally realized, hey, the carbonate crisis, the oxygen ultraviolet crisis, no matter what kind of evidence we got in here, and the evidence is very weak anyway, this can't be a sign of the origin of life. But yeah, these Europeans are kind of bringing back that old story, hoping that people have forgotten all this work that was done to eliminate ALH 84001. Yes?
More questions?
Yes, Hugh, what do they know? Do scientists know what happens after a black hole eats up the whole galaxy around it? Has that ever happened?
Well, there are
ideas?
supermassive black holes that have eaten up a good fraction of the galaxy. But you know, in order for the black hole to really suck something in, it's got to get relatively close. I can assure you there's no danger of our solar system being sucked into the supermassive black hole of our Milky Way galaxy. We're just too far away. But we are able to image stars that are right next to that supermassive black hole. There's about 30 stars. In fact, you can read an article. I wrote an article about a year ago about the stars that we're observing just outside the event horizon. We're able to measure their orbits. Interestingly, none of the stars that we're able to see just beyond that event horizon are at risk of being sucked in anytime within the next, say, 100 million years. So, and if you just do a search for supermassive black hole at reasons.org, the article will pop up and you can read it. Now, things are different in M87 because you're dealing with a supermassive black hole that's 2,000 times more massive. And so stars in its vicinity are indeed getting sucked in, and explains why it's such a very bright image you get outside that event horizon, and why you got this powerful jet coming out, and why it's really good that we're 50 million light years away. You don't want to be 20 million light years away. So, yes?
Here we have another question.
Okay, back to the idea of comparison of when quantum gravity effects become competitive with
Right.
gravitational effects, and I was wondering what the scale. For one thing, what's the scale of the quantum gravity effects, say, versus the scale of the gravitational waves? I mean, we know from the LIGO data the approximate size of the gravitational waves.
Right.
And so that, I guess, for quantum gravity, I'm trying to get at when the quantum gravity effects will be competitive with that. If there's a speculation or a known or a theory of the different wavelengths that might be involved there, so that we can determine when the quantum gravity effects become competitive with the gravitational effects. And also at the same time then, when you start talking about those, say, gravitational wavelengths, now we're talking about, I guess I'm trying to get at how we identify the edge of this black hole. And will we be able to identify it within our knowledge of the wavelength, or how do we do that? Thank you.
Okay, good questions. And you know, when I was talking about how if we make observations outside the event horizon, we might be able to determine something's going on in quantum gravity. If you actually get into the very center of that supermassive black hole, you got quantum gravity operating. You know, a question I got repeatedly on my Facebook and Twitter page was, well, can black holes stay black forever? Or are they like stars? There's a time limit. And I says, yes, there is a lifetime for black holes. Because what happens with a black hole is that they're collapsing under their own gravity. And they just keep collapsing and keep collapsing. These supermassive black holes, they're eventually going to collapse down to the size of an atomic nucleus. When they get smaller than an atomic nucleus, then that's where quantum mechanics actually exerts more impact on the dynamics of the black hole than gravity, which means at that point quantum tunneling will overcome the gravity. And so everything the black hole is sucked in eventually will quantum tunnel out, and that's what Hawking referred to as a white hole. I mean, of all the contributions Stephen Hawking made, that's probably the one I think is going to be his legacy, is he was the one who determined if you wait long enough, black holes become white holes. There's going to be a huge flash where everything trapped inside the black hole will quantum tunnel out. He also calculated how long that lifespan is. The bigger the black hole, the longer you got to wait for it to become a white hole. The smallest black hole we know of is about 4 times the mass of our star, the sun. 3 or 4 times the mass of our star, the sun. A black hole that tiny, you have to wait 10 to the 66 years before it becomes a white hole. That explains why we astronomers have never seen a white hole. We live in a universe that's ridiculously too young for there to be enough time for a black hole to become a white hole. The universe is only 10 to the 10 years old. So you got 56 more zeros you got to run into before you're going to see. And for the supermassive black hole, it's going to be a whole lot longer than 10 to the 66 years. So it's not going to happen in your lifetime. It's not going to happen in the lifetime of our galaxy. But that does kind of get at your point, is that the black hole has to shrink down to that small of a size before you're going to have quantum mechanics able to overcome the force of gravity. And you got to wait a long time. On the other hand, there's already stuff that's collapsed down to that side the black hole. It's going to give quantum gravity effects, which have the possibility, and I'm emphasizing that, there's no guarantee, but there's a possibility we'll be able to see effects outside the event horizon that gives us some idea what that quantum gravity interaction is like. So, okay, can we jump into Isaiah? All right. All right. Yeah, I don't have an, okay, here's what we're going to do. I want all of you to take, okay, I brought, again, I know this class. I have to keep handing these things out. So what you have here, and by the way, this is now online. We just put, so all of those of you who are participating online, we have a list of all the Isaiah passages written out. If you don't have a copy, take one, because I'm going to give you an assignment. Okay. This is going to be a little bit different than the questions. And by the way, if you don't have the questions, I've also got those here for you as well. The questions we have in Isaiah that we're looking at to integrate what Isaiah says about creation. But here we're looking at what the book of Isaiah says about the doctrine of the Trinity. And here's what I want to do. I want to form a group that's going to go through these passages and pick up all the texts that say that God is one and only one. So I want you to focus on the unity part of the Trinity. I want another small group to look through all these passages and identify all the passages that talk about God the Father. And then a third team is going to do the same thing, go through all these passages and pick up all the ones that talk about God the Son. And then another team, God the Spirit. Okay, I also want a team that's going to go through all these texts and find all the passages where it mentions 2 or 3 of the 3 members of the Godhead in that single passage. And what I'd love to do is by the time we're done, we're not only going to put up all these verses on the website, because what we got here on the website and in print here in the class are all the Bible texts, are all the passages in the book of Isaiah that pertain to the doctrine of the Trinity. I'd like for us to complement this with subsets. Subset 1, all the passages in Isaiah that say God is one and only one. There's only one creator. Another subset where we talk about the passages here that talk about God the Father, God the Son, God the Spirit, and then a subset of where it mentions two of the three. And incidentally, there are two texts in Isaiah that mention all three in one text, but we can make that a subset. And I'd love it if we can have all that posted on the paradoxes.org website.
These are left over.
Those are left over, good, and I got extra for next time that we get together. I'm also going to encourage the people that are participating online to pick one of these areas and do their own, because I'd be really interested if the passages they come up with are identical to the passages you here come up with. So we got enough time that we can form groups. And I want to get you into these different groups, and I want you to appoint a leader. I also want you to appoint a secretary. So what does the secretary have to do? The secretary actually has to write down all the passages. I don't just want you to discover these passages. Please write them down, and then I'm going to make you responsible as a team to actually get these in electronic form so you can put them on the website. And you say, Hugh, why don't you do this all on your own? I'm saying I think it'd be a lot more fun if you were to do it, okay? I could do it, but I really want you to have some of the joy of actually going through these texts and picking up these passages on your own. And not just those of you that are here in person. I want people online to be part of this too. But if you're online, pick whatever team you want to be part of, and then actually go through it as an individual and assemble the passages, and then find some way that you can email us at paradoxes.org with what you come up with. Okay, for the people that are here, who would like to be part of the team where you pick up all the passages where it states that God is one and only one? And by the way, we're going to limit it to 6 people per team. Okay? You want to be part of that team? Okay? We got Jim back there. Anybody else? You're going to be part of that? Okay? All right. We got 2 more. That's 6. We got the 6. Okay. Which of you wants to be the secretary? Oh, boy, this is where it gets tough, right? Because the first job of the secretary is going to be to write down the names of these 6 people that volunteered. You're going to do that? Okay.
Team 1 over here.
All right. Okay. So Ross Hoagland, go to him and make sure he gets your name to be part of that. Okay. Who'd like to be part of the God the Father team? There's a lot of passages in God the Father. Who wants to be part of that team? You're going to be part of it? Thank you. Okay, Gwen Ellen's going to need some help. Come on, she's not going to do this by herself. Okay, Mark Perez. All right, you're going to help. Can we have a couple more? I'd like to get 5 or so. Okay, we got 5. That's good enough. We got 6. Okay. Who's going to be the secretary? You're going to be the secretary. You're going to collect all the names of the volunteers. And by the way, when the class is done, go to your secretary. I want to make sure we get the names, all right? Okay, God the Son. Who wants to be part of the second person of the Trinity? All right, we got a volunteer there. Anybody else? Okay, thank you. 3. I want to get us up to 4. 1 more, 5. Okay, that's 6. Okay, who's going to be the secretary? You're going to be the secretary? Okay. See Mark afterwards if you're part of God the Son team. He wants to get your names. Okay, how about God the Spirit? This is going to be a fairly easy assignment. There are not too many Spirit passages. Okay, we got a volunteer here. Anybody else want to join the Spirit team? Surely there's got to be some Spirit-inspired people here. Anybody else? I mean, this is the easiest assignment of all, guys. So if you want an easy one, this is the one to join. We got 1 volunteer. We got 2. Anybody else? 2 may be adequate. I'm okay with 2 because, and you're going to volunteer to be the secretary, I hope? Okay. Go see him afterwards. And how about the team that's going to be part of picking up all the passages where it mentions 2 or 3 of the members of the Trinity in one passage? Who wants to be part of that team? That should be a really fun team. All right. I mean, this is a big class. Okay, we got a volunteer back there. Okay, anybody else? Okay, thank you. We need, okay, you're part of 2 teams, right? You're okay with that? All right, okay. I want to get, no, I don't want anybody kind of on the sidelines. Let's all get involved in this. I'd love it if you're part of at least one team, okay? So when we get together on this, I want everybody to join a team. So, but let's get a couple more for the 2 or 3. Yes, okay. We got 3. Do I see another hand out there? Okay. We got 3. Next week, think about what team you want to be on. I want everybody on one team. You're on 2 teams, and maybe we can find someone who will take your place so that you're just on one team. Because after all, we got a lot of people here. So yeah, your assignment, if you're not part of a team, when you come next time, you're going to be on a team. And if you don't choose a team, we'll assign you to a team. Nobody gets to escape this, okay? It's too much fun. You want to be involved in this. All right, and I'm encouraging all of you that are online to think about being, you're going to be the secretary? Who's going to be the secretary for the 2 and 3? We need a secretary.
It's not a big deal. All you do is just check the scripture.
All the passages where it mentions 2 or 3 members of the triune God. Okay, 3 of you volunteered to be part of that team. I need one of you to step forward and be the secretary. Who's it going to be? Oh, you want to join that team too? All right. Now I think, yeah, you're on a different team. How about if I make you the secretary? You okay with that? Yeah. All you got to do is collect the names of people that are part of your team. So anyways, we're going to close the class. As the class ends, go to your secretary and make sure they get your name. Okay, the rest of you that are not on a team, think about what team you want to be part of next time we get together. And if you don't choose one, we'll choose one for you. Okay. Let me close in prayer, and and by the way, we got to be out of here within 16 minutes. So we can talk outside, we can talk in the parking lot, we can talk on the hallway here, but we got to get the chairs at the back because we got another group coming in here in just a few minutes. And is this going to be the way it is every Sunday? I don't think so, but bear with us as we try to get things dealt with. Father in heaven, we want to thank you for just an amazing week where these incredible discoveries have been made in your book of nature. And Father, we thank you that you've clearly revealed yourself through the book of nature. And every day you're giving us more revelation of who you are, your characteristics, and your plan of salvation. And Lord, I pray that you'd equip us here in this class to be able to use what you reveal in the book of nature to encourage people to look at the book of Scripture and to see what you revealed there about your sacrifice. We thank you, Lord, that next week we get to celebrate that not only your sacrifice, but your resurrection bodily from the dead. And we thank you, Lord, that even 2,000 years later, we have such overwhelming historical evidence for that bodily resurrection from the dead that it's actually stronger than almost everything else we learn about in our history textbooks. So, Father, I pray that you give us many opportunities during this Holy Week to be a bearer of your good news, the good news that you came to this planet, the creator of the universe, humbled yourself as a human being, and in that form paid the penalty for all the offenses and evil that every human being has ever committed, and have made an offer that if we will make you the master of our life, you'll give us complete deliverance from all the sin and evil in our life, past, present, and future. Thank you, Lord, for doing that for each one of us. And I pray, Father, you'd encourage those of us who have already done so to invite others to join us in receiving of that amazing gift. In Jesus' name, amen.